Hello everyone, Benny here, and in this video with any luck, we're going to be finishing the computer in this video. So, let us begin. First, you don't need to technically do this, well what I'm doing right now, but I am going to go ahead and do this anyways, and the reason I'm going to do this is because, well, it's just going to make our computer easy to use. And that's like the whole point. It is going to slow things down a little bit, but not too much. And that's why, really, I'm going to do this. So hang on, first I need to test this, make sure that this is still working, and just barely not enough. It's okay though. It's okay. We can fix that. Okay, so there we go, very first one. And now we just need to complete the wire. And I haven't even finished extending it out yet. That's okay though. Okay. So this is going to be a command to begin accepting instructions. And I may move this later. In fact, I am going to move it. I'm going to move it to right here. So first off, I'm going to move it out a little bit, just in case I want to add some more commands later on. Though I really don't think I will. This is going to be like our primary control panel, right here. Oh yes, and I am aware that I didn't really do any explaining whatsoever about what on earth we did in the last video. And the reason is it doesn't make any sense until it's completely done. So I'll do a brief explanation in this video, and if you want a more thorough explanation, again, we're going to have an explanation video. So yeah, anyways, we're extending out the wire. Yep, nothing special. Hopefully you know how to do that. Okay. Now, I would like to point out that we are going to have a slightly, I guess you could say inferior control system. And the reason for that is, well, I've said throughout the whole series that this is supposed to be an entry-level computing device, so that's the reason. This is supposed to be entry-level, and this is pretty much the easiest way to keep it that way. So, there we go. So this is, we can make this even easier so that the person doesn't have to see the redstone. There we go. So this is going to be our start program command. It's going to be part of the user input, and whenever the computer is on, and they can say start the program. So that's enough for now. And this is going to be the on/off switch. So yeah. Oh yeah, and one convenient thing about this design is that it automatically resets the program every time you turn off the computer. So we don't have to worry about any interesting handlings for that. It's already handled for us. So now I am going to go up a little here, just to try and keep things separate. Okay. Now we're getting to an interesting point, so I'm going to build this thing over to this. And this is probably going to be enough space, so I'm just going to go ahead, say, do it. Build snow, okay. Now what I'm going to do here is I'm going to build a monostable circuit. Hopefully you know what that is. If not, basically it only allows a small pulse to go through the system. So the way this is going to work is I'm going to have 2 repeaters here at a 6-tick delay, and I can do it, so put a torch here, and we're going to take power over that. And now what this can do is every time we hit this, if we just flip it, it only allows a short pulse rather than the whole thing to just go on forever. So this is going to be the basis of our clock. build a clock. We will only need 4 repeaters, 1, 2, 3, 4, and a piece of redstone. Oh yeah, and of course a torch. Now, by default, this is going to be already running. I don't necessarily want that, so, to fix that, I guess you could say, actually, I don't know if I could really fit the clock here, because this is causing some issues right now. This is causing some serious issues. Because I need the wire to go this way. And okay, what I'm going to do is I'm just going to change the orientation of the clock. Because I can't make it face that way. But that's... Oh... Also, make sure you do your repeaters in the right direction. That's a pretty nice thing to do. So yeah, okay. So now here's our clock. Here's our clock input. And awesome, so whenever so right now I'm just going to go ahead and make it not work. And the reason for that is I don't want this thing to to just instantly be on all the time and doing everything. So that's, can I still? No. Can I? No. Okay. I'm going to make it go this way. And after some interesting wiring maneuvers, we have our clock wire mostly set up. The clock does take an inverted input to turn on, so we will have to invert this. And the easiest way to do that is with an inverter. So, I am going to flip it, see what happens. And right here, since it's perfect, I'm going to put an inverter. There we go. Now I just need to start adding repeaters so that it reaches. And now I can get rid of that temporary, this temporary lever. Okay, so now, this is basically our computer completed. So if you've made it this far, then congratulations, because this is quite a milestone. So now, I'm going to just add a quick little floor in here for our user. And I'm actually going to move back this way a bit, because why not? So from here to here, fill with snow. And whoa, no. There we go, much better. I, really hope that didn't screw anything up. It has a mild probability of doing so, but oh well. Oh, I just noticed a problem. We can't do this. So, the way I'm going to fix this is I'm just going to make a simpler monostable circuit. This hopefully is still going to supply enough delay. Just going to temporarily start our clock. And realize that I did it wrong again. That's okay though. So right now our clock's moving way too fast. I'm just going to set it at maximum delay for now. We can go ahead and time the amount of time it takes to process this later. That seems like a really, really fast pulse. And these things don't seem to be working either. Huh. Okay, this is probably going to cause some issues. So to fix this, that's the real question, isn't it? Okay, to fix this, first off, I'm just going to move everything back. Whoa. And don't worry, after this thing will be completed, so. Okay, hang on. I am not here's an easy way to fix it. I'm going to start with my torch here. There we go. And it does have enough to... And it is picking up the, what's it called? The signal, so I don't need to worry too much about that. So... add a torch. And now we have monostable circuit. And it is accurately receiving what I seem to be putting in. Perfect. So, okay, now I just need to, yeah, okay, there. Now that the whole system is finally set up and working, we can start testing this. So, we only have one program on it, which we haven't written, but we'll go ahead and do that in a bit. So right now, we'll go ahead and turn it on. And now our computer is on. Every so long, it is accepting a new command. And that is at maximum delay, I'm pretty sure. Yeah. That should be long enough delay for our computer. If it's not, then dang. I mean, I know I slowed it down a bit to make it easier to understand, but hopefully I didn't slow it down that much. And right now, it's not accepting any program, because I haven't told it to start the program yet. So if I say start program, you should notice that there is power going to this wire. And that's good, because there should be. But it also means we need repeaters, because I neglected to add them for some apparent reason. So yeah, we're just go ahead and add repeaters, not there, but to all these top wires. And okay, there, that reaches. Now I did notice a slight issue, and that is these wires also take an inverted input. So I need to fix this, because this... And I have an idea on how I could fairly easily fix it. Except... I think this is going to screw up the clock. Actually, wait, no it doesn't. So basically the idea is... at some point, such as this point, we just invert the what's it called, the go-to command, because that's what these four wires are. They're the go-to command. In case you didn't know. If you didn't, hey, now you do. First, I just need to reorganize this slightly, or else F interference and. There we go. Now that that's... has not solved my problem in the slightest. And also it's finding this one for some reason. Is this, oh, well, this would be a very good reason why this wouldn't be working right. Yeah, that didn't solve my problem. I'm sorry that I do have to do a little bit of, I guess you could call it redstone trickery to get this thing to work. But, okay, that's working. I think I can go ahead and solve this, because I have a pretty good idea of how I can. So, these things do need inverted inputs. The way that I can hopefully fix this is by doing one of these, and it's going to slow it down a bit, but I honestly don't care at this point. So, that's not going to screw anything up if I copy it like that, so 1, 2, copy, yeah. And, whoop. Okay, that's going to be easily fixed. And yeah, I'm really just want this thing done now. This may be the longest video in the series, but that's okay, because this is hopefully the final video. I'm really trying to make this go ahead and be the final video. So, yeah. Okay, I was hoping I didn't have to do that, but oh well, I do. So, what do you know? Alright, now we can go back to our user control panel and turn it on. So, now it is running, and all the commands have their inverted input. And again, I'm still going to go ahead and explain that after this thing starts working. So if I do that, that turns off, which is perfect. Now, I can finally explain what on earth is going on here. Each of these lines is going to be a program command. Basically, each of these lines is one programmable line of code we can give to the computer. And I will show you how to do that in just a short bit, if you don't mind. So, that's the way this works. So this is line 0. The computer always starts on line 0. No matter what you have in your computer, it always starts on line 0. This will be like our startup instructions. And then, from there, we can program it using the goto command, as I referenced earlier, to choose where to go. Now, this is usually something you want in a more advanced computer, because in just our computer, I mean, typically you don't care that much about, well, about having to go in an explicit dynamic order, I guess you could say. You would really normally just have set up to go to 0, 1, 2, 3, 4, 5, 6, 7, 8, not 0, 8, 2, 4, and some other crazy combination. If you want to do crazy combinations, you'd usually have conditional branching, so you could set up, okay, do commands 1 through 3 over and over again until something happens, and then go to command 4. And that's a way to do a whole bunch of stuff with a single command, but yeah, that's really just advanced programming stuff. That's the reason we have this, and that's the reason we have the decoder. The decoder finds which command we're telling it to go to. And when this wire is receiving power, when this wire is not receiving power, that basically turns all these wires on, which means the computer isn't taking in any commands, not doing anything. And our clock, well, this basically determines whether our computer's on or off. We just set it up so that every time the clock takes a pulse, it goes to the next command, and then we'll read that out and do everything with the computer. And I'm still concerned that the clock might be too fast right now. But hopefully that won't be an issue. In fact, just to make double sure, even though I'm still pretty sure it won't be an issue, I'm going to extend out the delay of our clock even further. And yeah, that is a long time to process. So right now our computer will run really, really slow, unfortunately. But that's okay. So now we have a computer. So now it's time to program it. Okay, we're back. I'm sorry about that. And now it's time to program it. So, first thing I'm going to do is I'm going to add some new hardware to our computer. Not completely sure where I'm going to add it, but basically I'm just going to set up a binary output. So this is just a place we can send an output so that we can display it. At least that's the idea. Now I'm going to make sure to actually select so that I don't accidentally knock out all my signs again. That was fun. But anyways, so just gonna go ahead and do this, and now I should label them. So 8, 4, 2, 1. And this is going to be our first optional expansion slot hardware. So we can expand to have, well, first I'm going to just make sure that I know where they are. Blocks. And yeah, so this is going to be our first optional expansion hardware. So I know this is 1, so I'm just going to sort of derive where this should be. So this is 1. And 1 goes over to here, I'm pretty sure. Yeah, so just connect 1 to 1. And all the usual stuff. Hopefully you know how to do this anyways. Well, maybe not. I don't know. Maybe you don't. Okay. Because I'm having some surprisingly severe difficulty doing this. So this is the way I'm going to do it. Now this should turn off all the torches. So this is a binary output. Just a piece of hardware we can use, we can leverage. And, oh, that's our underground system. We don't need to worry about that. This is 8. I'm just going to go ahead and connect 8 to its system. So there is 8. And yeah, okay, there we go. Just connect them to their correspondent systems now. It's not particularly difficult as long as you keep your spacings right so that that doesn't happen. And of course it's always good to double check repeaters after this, so that's what I'm going to do. After this we can finally start programming this. Wow, it's been a long time coming. So, let's just look at it. It's turned on everything except number 1. It's literally 1 off from reaching 1. Wow. That's okay, we can add a minor delay for the 1. It's not gonna be the end of the world if we don't get our 1s out instantly. Okay, finally we have an binary output, we have everything set up, we can start programming this. So first off, I should explain how programming this thing works. Again, each of these lines is a command, and as you know in computers, a command is a string of 0s and 1s. So the way this works is nothing there is 0, a torch is 1. So 1 is do it, 0s don't, pretty much. So let's go ahead and get started. First, I'm going to program it to go through the commands in order. This is going to be our first program. It's going to be so exciting. So this is a go to command right here. There's bit 1, 2, So basically right now I'm just counting up in binary using torches. 3, 4, 5, 6, 7, and I think that's far enough. After that it goes back to program command 1, so it should be doing a big giant loop. So go ahead and turn it on and start the program, and the way it should just keep going down the line. If our clock, holy crud, that's a long time. But it is still working. So I'm going to go ahead and turn it off now that I know it's working. And again, this thing's going to move really, really slow until we optimize the clock. But now, first thing I want to do with the computer. On command 1, I want to set up the general indicator. All that's going to do is it's going to tell us that the program has started. So, well, in this case it is. General indicator is general. It can mean literally anything. So now, what I'm going to program it to do is add, because that seems to be the hello world program of Minecraft computers for some reason. So, yeah, we're going to program it to add. So, what do we need it to do? First off, we want to get user input from number 1. So I want to read from ROM somewhere. Read ROM 0 is user input 1, that's good. I want to send RAM, which actually should be send memory, but send RAM as AOU input. And send AOU as input A. Cool. I'm pretty sure that's everything we need to do this command. Yeah, we're not dealing with RAM, so this is our completed first command. Next command. AOU subtract, read ROM, okay, so now you need to read ROM again. We're going to want to read the second user input, which is done with 1. We want to send that as an AOU input. I'm going to send that as AOU input. Oh wait, whoops. Send as AOU input. I'm going to send that as input B. And now what we want to do is, we're again programming it to add. So if I can get out from under this, add on command 3, we will add and send that to RAM. So write RAM. It doesn't matter where I write it, so I'm just going to write it to RAM 0. And you know what? I can go ahead and do this all in a single command. So write RAM and reading command. And after I read it out, I want that to go to the expansion slot. So there are expansion slots. Expansion slot 1, that's where we have that plugged in, so I'm going to send it to expansion slot 1. Now I'm going to break these go-to commands, because that, actually, I'm going to write that to go-to, so that's just going to keep it locked on the second command after on the final command. Oh yeah, and might as well just general indicator to show that it's done processing. So, we've set up a program. Let's do 2 plus 2 with this. Let's turn it on, and it should be on, and it is. So, let's start the program. And we get the general indicator, and we get those off signifying that it's reading it. And we get that signifying it's got the output. And it gets a 4. It's exactly what we wanted. Now, again, I can do more addition now. These particular torches are off for some reason. Why on earth? Oh, right. Whoops. That was me just not thinking. The whole purpose of these torches is to let the user know that, hey, the computer is currently doing something with this information, and that still doesn't work. So, try not to do anything, but it's not seeming to be working particularly well with the way I have it set up. So I'm just gonna... Actually, okay, there. This has gotten outrageously complicated, but this is not at all the most efficient way to do this. So now we know if it's accessing that, and I'm going to relocate this repeater because it's not particularly important. There we go. So now that display is working as intended. So we did 2 plus 2, you know that. So I'm going to turn off the program. Boom. It's unloaded the program, and now it's still on, so we can still do stuff. So let's do 5 plus 3 with our program. Start. Stand on indicator till it's on. It's on. It's going to the next command, and we should get an 8. Yep, there we go. We got an 8. And of course, it's going to stick there because that's what we programmed it to do. So, let's talk for a minute. We've just completed the entire computer from start to finish. And while I'm doing this, I'm just going to go ahead and make it run the program again so you can see that these things are working. So, this is, I think, a significant accomplishment. Because, I mean, if you've made it all the way through the series, seriously, congratulations. This has been quite a project. But, you've gotten through it. If you are sitting here, you have gotten through this. So, now, congratulations, good luck with your computing endeavors. I'm going to add more videos later, not necessarily this series, because this series is now over, but about other tips and tricks to making a computer that's not quite as slow. So, and maybe just making things better in general. And some interesting redstone computing parts in general, maybe just general redstone machinery, depending on how I go with this. So that's my current plans for this, so without further ado, this series is over, so let's have some fun. Let's overclock our computer. And basically what we're going to do is we're just going to overclock it until it's running so fast that it doesn't work anymore. So let's start the program and see if it still comes up with 8. And it gets us not 8. So we've already overclocked it to the point where it's too fast. That is great. Just one step, boom, it doesn't work anymore. On the plus side, it's pretty fast, I guess. Well, this isn't... Okay, yes, this isn't a particularly fast computer. But oh well. So, let's just find how fast this thing can go, because I didn't think it would be this slow. I mean, I know it was going to be kind of slow. I didn't think it would be this slow. Let's try again. And it doesn't even seem to be working at all. Oh, no, we got an 8. Hey! We've gotten an 8. And, oh yeah, well, I forgot. So the reason this may have not been working is because you want to do the delay in the center, if you can, because of the way that clock design works. So this still has hope. Also, this design also amplifies clock delays, so that's another reason this might not be working. Hey, what do you know? That was the reason that wasn't working. So this thing isn't as slow as I thought it would be. So see, we got a nice little system set up here. So now this is the next thing we can slow down. And again, that's double the delay, so that's actually 6 ticks we're taking off because of the way the clock design works. So now we're going to test it again, see if it can work. If it comes up with 8, I'm going to be amazed, quite honestly. Oh yeah, there's no way this is going to... what do you know? It is... Wow! This is a really fast software error. This actually might be faster than the one in my other series, because I thought was so fast. But that just shows you. It does happen. So now I think that this one should be the one that's good to remove if we're going to overclock this even further. And if this thing still works, I mean, man, I'm gonna be really surprised. But start the program. On. Off. Yeah. Oh my god, if this thing works, I am going to be... Wow. Seriously. I am impressed. I am really, really impressed that this thing is moving as fast as it is. And I don't think I can safely overclock it any faster than this, even though this is still a pretty fast clock. So, I mean, it's could be probably be a little faster. I think this is going to be safe. So, oh my gosh, we're going to try it even further. We're going to see if we can overclock this thing even further. So I'm going to unload the program. Load the program. And if this thing works, oh my god. Oh, nope. Nope, nope, okay. Okay, I knew I was pushing it a bit there. But, you know, we can still try to make it a little bit longer. We can see just how fast we can make it before it stops working, because, yeah, you never know. You never know. That's the thing. So, let's start. And, yeah, I didn't think that was going to work properly. Oh well. And ideally you wouldn't be testing the clock speed like this. Ideally you'd be doing the most complicated operation the computer could possibly do, i.e. not addition, and then basing the clock speed on that, but I'm just curious now. I want to see how fast I can make this go. So it's, hey, there you go. That's as fast as we can make it go. I still think that's pretty fast. So, yeah, there you go. That was just goofing around. There was no particular point to that. And just for fun, I'm going to do a different addition. I can do a more strenuous addition, so I'm going to do 7 plus 1. The reason it's going to be extremely dangerous, not dangerous, but it's going to be slower, is because it's doing a full ripple carry. So this is worst case scenario addition, and this might not work, but it does. That's the thing. I want to run this again just to look at the lights while it's doing it. Load, load, boom. 8. Oh, hey. So no, it doesn't. It does need the extra delay. So there you go. That's as fast as it can be. It's a total of 4 plus 4, 8, 12 ticks. 12 ticks in a sequence like that. So that's a pretty fast clock. 12 ticks. And let's start again. So this is really the worst case scenario test. And we get 8. Hey. So there you go. That's as fast as it can go. That was just for fun, because the series is over, pretty much. So we're just sort of goofing around a bit, having some fun. And in hindsight, I might have not wanted to put that thing all the way over there, but oh well. This design works. Turning on, turning off isn't the most critical thing to the computer's usage. But yeah. There you go. Whole thing done. Just for fun, just for fun, I'm gonna go ahead and program to do subtraction. So I'm gonna have to reverse these. Let's change this to 1 and this to 7, and I'm gonna change it to do subtraction. This command, is it 2 or 3 where it does it? Oh, I should probably unload the program before I modify it. That can cause serious issues if you modify a program while the computer's reading from it. So send ALU, I think that should be over here. And again, this is all just for fun. There's no real reason. Okay, yeah. So there you go. Now we're doing subtraction instead of addition. Hopefully you have the good sense to not try and do and subtraction at the same time, or you get some issues. But, start program. Let's see, so it should be 6. And you get a really, really weird answer. I don't know if that's because it's too fast, or because of other... Wait. 7 minus 1. Yeah, that should be... Here, let's do something simpler, because I'm not entirely sure if I'm doing this correctly. So it should be loading this first, the second. So, let's try this again. Unload the program, and that might have been not long enough for it to unload the program, unfortunately. So it might still screw up. Oh, no. No, oh yeah, no, it's still screwed up. And there you go, giving plenty of time to unload the program. And... yeah, hey, what do you know? So there, if you give it enough time to unload the program, it can do subtraction pretty well. And just to try that again to make sure it's still not overclocked to the point where it doesn't work anymore. Just one more, it should be 6. And oh well, it is overclocked, but to the point where it doesn't do subtraction correctly. Subtraction is slightly more processor intensive. Not much, but enough. So just to be safe, I'm gonna add an extra tick of delay. So this theoretically should be... So actually, I should go ahead and set this up to the most intense possible setup. Or is it just giving me the wrong answer in general? Oh no, I unloaded the program. Never mind. It's giving me... Actually, this is... this does seem to be giving me Huh? This is... I may have screwed up my subtractor at some point, even though I don't see where or how, but oh well. It's not oh wait, hang on. What's my input A? Oh well. I don't know. Something is screwed up, and just to be sure this isn't the subtractor. You know what? I'll figure it out off camera and show you what's wrong in some extension videos. So, there you go. That was a computer series. Thank you. And thank you for completing the series. And see you next time. Hey everyone, I'd just like to make a quick extension to this video of why on earth that subtractor was screwing up. And well, there are 2 issues with it. First issue was hopefully you didn't, but I personally had forgotten to place these torches on this wire. That was causing some slight issues. I also am pretty sure I forgot to add repeaters to this wire for some reason. Not quite sure how that happened, but yeah, I'm just gonna go and quickly do this. But yeah, somehow I just completely forgot about this wire even existing. So, yeah. There we go. Problem 1 solved. Second problem was I was not paying close enough attention to the way my program was handling the command, so that this user input 2 was actually input A and user input 1 was actually input B. So the 8 and 2 that I kept getting from 7 minus 1 was actually 1 minus 7, and 8 and 2, well, in binary, that is, well, if mathematically that would be -6. And in binary negative 6 is 8 and 2, so that it was doing all the math correctly. I was just giving it the wrong information. So, just to prove to you that it works now, so what I did is I changed move 7 over to user input 2 and 1 over to user input 1. And now if I run it, and I'm running it at the same speed I showed you in what's it called. Oh, so it just worked, so I guess I do need an extra tick of delay. Unfortunately. But yeah, change the clock speed back to what it usually was. Just adding an extra tick right here because, yeah, it was not working, I guess. I mean, add an extra tick because it wasn't working. I'm sorry, I'm a little confused right now. That's okay. So now it should give me the correct answer of 6. And yeah, it does. 7 minus 1 is 6, and yeah, that's everything for this video. So, again, thank you. See you next time.